Hello, everyone. Welcome to today's seminar. And as usual, my name is Shuan Li, and this time we are very glad to have Professor Jinhong Yuan from University of New South Wales to share some of the recent findings on ODDM. I'm going to give a really quick, brief introduction of OTFS-SIG. If you are interested in this technology or in general delayed Doppler multi-carrier modulation, please join us. And today's talk will be given by Professor Jinhong Yuan on the topic of characteristics and performance of ODDM waveform over general doubly selective channels. I'm going to give a quick introduction of our old friend, Professor Jinhong Yuan, who is also my PhD supervisor. Professor Jinhong Yuan is an IEEE fellow, and he has received a bachelor and PhD degrees in electronics engineering from the Beijing Institute of Technology in 1991 and 1997. From 1997 to 1999, he was a research fellow at the School of Electronic Engineering, University of Sydney, Australia. In 2000, he joined the School of Electronic Engineering and Telecommunications at UNSW, Sydney, where he is currently a professor and the head of the telecommunication group. He has published 2 books, 5 book chapters, and over 300 papers in telecommunication journals and conference proceedings, and 50 in industry reports. He is a co-inventor of 1 patent on MIMO systems and 4 patents on LDPC codes. His current research interests include error control coding and information theory, communication theory, and wireless communications. He has co-authored 4 Best Paper Awards and 1 Best Poster Award, including the Best Paper Award from ICC, Best Paper Award from IEEE WCNC, and also the Best Paper Award from IEEE ISWCS. He served as IEEE NSW Chapter Chair of Joint Communication, Signal Processing, and Ocean Engineering Chapter from 2011 to 2014, and served as an Associate Editor for IEEE Transactions on Communications from 2012 to 2017. He is currently serving as the Associate Editor for IEEE TWC and TCOM. Okay, without further ado, please join me to welcome Professor Jinhong Yuan for today's wonderful speech. The stage is yours, Professor Yuan.
Okay, thank you. Thank you, Shuan, for your nice introduction. Thank you, everyone, for your invitation. Can you hear me clearly?
I think so.
Yeah, okay, I'm going to share the screen. Can you see the shared screen?
Yes.
Okay. Go to the presentation mode. Okay, yes. Okay, good afternoon or good morning. It depends on where you are. And today I'm going to talk a little bit about our recent work on ODDM waveform. And later on, talk about the characteristics and the performance of ODDM over general doubly selective channel. Obviously, this is a joint work with my postdocs, PhD students, and collaborators, and also some contributions from my former students and postdocs. So this is a pretty simple outline. First, try to briefly review what is ODDM, orthogonal delayed Doppler division multiplexing. Later on, we are going to focus on a few interesting properties of associated with ODDM waveform. One is time frequency localization. Second one is how to implement ODDM, and either in analog form or in digital form. Then we talk about the time and the spectrum response of these ODDM signals by using different implementations. Finally, we have a look at what is the performance of ODDM over these general channels and its effect of channel state information on the performance. So yeah, starting from the ODDM. And ODDM obviously is a delayed Doppler modulation, and it could not be here without the key topic is OTFS. Actually, ODDM is motivated by looking at the OTFS and the delayed Doppler domain channels. So after that, we talk about what is a key component of the ODDM is the delayed Doppler orthogonal pulse and the DDLP, then try to link the delayed Doppler domain modulation to the conventional multi-carrier modulation. How can we look at it from different angles or different point of view, and then take a look at how can we multiplexing signals in general in the DD plane. So obviously in for 6G and the future, and the people are talking about the high mobility communications, as is a high speed rail, or it is integrated sensing and communication. Or if this is not in 6G, but also for underwater communications, you have this high Doppler shift or high Doppler scaling, depends on the use scenarios. So there need waveform which can support high reliable communication in all these scenarios, such that we can have reliable and communication in the meantime with have low complexity transceiver and high data rate. So the question we are focused on is there any waveform can better interact with wireless channels? What do we mean by better interacting? Means robust and reliable performance, and also have viable choice and over doubly selective channel for future scenarios. So OTFS came with very timely in 2017, proposed as a new two-dimensional modulation technique. It works very well in high Doppler environment, particularly if your channel has selectivity in the time and is due to the mobility and also selectivity in the frequency due to the multi-pass propagation. So the key idea of OTFS, and the OTFS representing, I think everyone knows, orthogonal time frequency space modulation, to try to exploit underlying delayed Doppler domain channel properties, including compact channel response, if you have a delayed Doppler domain spreading function, sparse if you have a few multipass there, also a stable behavior, which is described by the stationary behavior of the delayed Doppler shifts. So if you can carry information in the delayed Doppler domain, you probably can couple the delayed Doppler domain channel more easily. So the OTFS aims to have a minimum crossing interference, and in the meantime, to have full diversity in the delayed Doppler domain and high reliability. So if we talk about the delayed Doppler modulation, we cannot ignore the delayed Doppler domain channel. Conventionally, if we have a time variant channels, we usually look at the channel in the time frequency domain. You have this time variation in the time and the time variation in the frequency. We have a coherence time, coherence bandwidth. Typically, if we have a carrier frequency 5 gigahertz, and if you drive a car at 120 kilometers per hour, typical coherence time is 2.5 milliseconds. So what does mean? Means if you use transmission frame, your frame size must be less than the coherence time. So you can estimate the channel more reliably during that period of time. But if you look at the channel in the delayed Doppler domain, we have a different representation of the channel. Is called the delayed Doppler spreading function or spreading function. So it is classified as number of passes P. For each pass, you have its corresponding attenuation HP is a delay tau P, and it's a Doppler nu P. So you have this determines the channel. But more importantly is if you have a look at the channel in the delayed Doppler domain, and the number of passes does not change very quickly, as well as its associated delay shift and the Doppler shift. In other words, if we look at the stationary region of the channel, the delay and the Doppler does not change within a kind of 10 times of your coherence time. And given the same carrier frequency 5 gigahertz, if you have a car transmitting to a base station, the car is running at 120 kilometers per hour, the stationary time is 1.5 milliseconds. If you look at a much severe situation, say you have two cars and running at two opposite directions, each of them has 120 kilometers per hour, your stationary time is still 23 milliseconds, which is 10 times of the coherence time. So if you look at this coherence time, coherence bandwidth, stationary time, you can see in time frequency domain, the channel is changing very quickly, is density, and you need more resources, and you need a frequent channel estimation. In contrast, in the delay Doppler domain, you have this compact, sparse, stable channel, allow accurate and low overhead for channel estimation. So there's a paradigm shift to look at the design communication system or the modulation, or even consider signal processing techniques from time frequency domain to the delay Doppler domain. Look at from the coherence region of the channel to the stationary region of the channel. So that is a little bit of background. Now, if we look a little bit further, what is OTFS? OTFS was originally proposed as a delayed Doppler domain modulation. And in order to coupling the signal to the delayed Doppler domain channel directly, you need a delayed Doppler domain localized pulse. But we know a delayed Doppler domain localized pulse would violate Heisenberg uncertainty. So as around the solution, OTFS circumvents this by using a 2D pre-code, means you have a two-step approach to generate the transmitted signal. Means if we have a conventional multi-carrier modulation, shown in the block diagram is blue time frequency domain multi-carrier modulation. We have this delayed Doppler domain to time frequency domain to the orthogonal pre-code. Because delay to the frequency is FFT, and the Doppler to time is another inverse FFT. It's a two pairs of FFT. People call it the inverse symplectic finite Fourier transform, RSFFT. So if you do this one, you can have a two-dimensional delayed Doppler domain modulation, and to transmit the signal, carry signal in the delayed Doppler domain, but in fact, you have an orthogonal transmission in the time frequency domain. There's different varieties about this delayed Doppler domain multi-carrier modulation. For example, you can use OTSM or other orthogonal transformations. So that means there's a one-to-one correspondence between the conventional time frequency domain, right at the right-hand side on this slide, and the delayed Doppler domain, and on the left-hand side. Say, on the right-hand side, if we have a frame structure, typically for our 4G or 5G, and each time frame has an n time slot. Each time slot has m subcarriers, and each subcarrier has, subcarrier spacing is 1 over t, is the inverse of time slot length. So you can have this orthogonal between different subcarriers. That is what we have in all FDM signals. Although you carry mn symbols over this nt seconds, m over t hertz of bandwidth. So given this total time frequency resources, actually you have the delay resolution is inversely proportional to the bandwidth T of m. You have a Doppler resolution inversely proportional to the total time duration of the signal. So we have this left-hand side, this delayed Doppler domain, fine grade. So if you look at, say, if you want to do delayed Doppler domain carrier modulation, obviously, each of this delay, you have multiple small grades. Excuse me. So you can easily do a multi-carrier modulation over the Doppler. Then you multiplexing the signal over the delay. So that gives us a hint how we are able to do orthogonal delayed Doppler domain multi-carrier modulation. But that is not what OTFS is initially proposed. So OTFS initially proposed is pre-coded OFDM still use the rectangular pulse for each time slot as widely adopted in the OFDM and OTFS literature. So the advantage is you have orthogonality in the time frequency plane. What do you mean full orthogonality? It means regardless of the number of time slots, regardless of the number of multi-carrier signals, you have these signals are orthogonal in the time frequency plane, but not necessarily have to be orthogonal in the delay Doppler plane. So you have this ambiguity, this OTFS signal waveform. You have this ambiguity on the right-hand side. It's orthogonal with time resolution t, time slot, and the subcarrier spacing 1 over t. But they also bring some drawbacks. One of the drawbacks is rectangular pulse may not couple effectively with the delay Doppler channel. Another one is if you use rectangular pulse and do not have this CP for each time slot, you may have high out-of-band emission if you not carefully design your signals from one time slot to another time slot, because you don't have this guard space between that. So that is one of the issues. So taking inspirations from this OFDM multi-carrier modulation, also the delay Doppler domain modulation principle from the OTFS, we propose this ODDM, orthogonal delay Doppler domain multi-carrier modulation. One of the key is it has to be multi-carrier modulation in the delay Doppler plane. So you need a pulse that has a fine delay and Doppler resolutions. That is, we want to carry the signal. In the meantime, you should not violate Heisenberg's uncertainty principle. So at the end of the day, we have this transmitted signal, ODDM. You carry the signal message XMN with your delay and the Doppler grade, but you have this transmitted pulse, UT, is orthogonal with the delay T over M resolution, with the Doppler resolution 1 over NT. So that is our delayed Doppler orthogonal pulse used to carry each of the message for the delayed Doppler modulation. If you look at what is the details of this DD or P, actually it consists of a train of en route Nyquist pulses. They spaced each of this is a UT consists of n sub-pulses. Each sub-pulse AT is spaced between with a t second, means between different time slots. Each of this sub-pulse AT is a root Nyquist pulse. We will later explain why we need to have this root Nyquist pulse. So compared to the pulse used to OFDM and OTFS, this pulse is orthogonal with respect to the delayed Doppler resolutions in the DD modulation. But it is only orthogonal within the given resources. So if you need to specify the number of time slots, and also you need to also specify the number of delay versions M. So it is only orthogonal given the bandwidth and given the time duration. Outside the resources, they are not orthogonal. So this is different from OFDM and OTFS. OFDM and OTFS, although they are orthogonal within the given resources, but they can be orthogonal outside the resources if they need to be. But here, we only provide orthogonality within the given resources. The right-hand side of the figure shows the ambiguity function and for the delay and the Doppler, and specified from the left-hand side. So if we look at the history, OFDM and is a multi-carrier modulation. If we generate a multi-carrier modulation from the conventional way, if we have a time slot of t and we have a subcarrier spacing of f is equivalent to 1 over t, and the rectangular pulse is used to generate each OFDM symbol. So that is one OFDM symbol. Then if we want to generate another OFDM symbol, and we keep going, and one after another concatenated, there's no overlapping. And in reality, we have the CPs in between of that. So that is a conventional OFDM as a multi-carrier modulation. I would like to also point out ODDM actually is a time-fixed multi-carrier modulation, but it is orthogonal with a fine time resolution, specifies the delay, and also fine frequency resolution specifies the Doppler. And we have a pulse train as our prototype pulse or fundamental pulse. In contrast, in OFDM, you have this rectangular pulse. To visualize the transmitted signal, let's say that is our total time duration NT, which we want to generate a multi-carrier modulation. So the subcarrier spacing should be 1 over NT, similar to the conventional OFDM signal. But here, in order to generate the signal, rather than use a rectangular pulse, we say you can use any pulse as long as it's periodic. If you tell us there's n subcarriers, as long as the pulse is periodic with n paired, the generated signal will be orthogonal with each other. So that generalizes the conventional multi-carrier modulation. I think that is different from the conventional multi-carrier modulation. It's designed based on the frame theory, and it guarantees global orthogonality. But here we say, not necessarily you have to be rectangular, because rectangular is only one if the number of subcarriers is any number, 2, 3, 4, 5, 6, or 1,000. But here we say, if we know the number of subcarriers n, the transmitted pulse or prototype pulse can be any pulse, as long as the pulse is periodic with n pairs. Here we show a particular pulse to generate an ODDM signal. So that's the first thing we would like to share with you. Second thing, say, if we have this, if we have this signal, it is a multi-carrier signal, we generate this, we use this a train of n sub-pulses as a prototype pulse to generate one multi-carrier signal. We can also multiplexing another one with a slight delay over t specified by t over m to multiplexing another multi-carrier modulation. So we keep going. So we can multiply m multi-carrier signals. Each multi-carrier signal has n subcarriers. So you have the same number of symbols, mn, to be carried, but we use different pulses. We use a different subcarrier spacing and different waveforms to generate the signal. So that is ODDM. So for the first signal, for the first multi-carrier signal, they are multi-carrier signal. By nature of the name, they are orthogonal with each other, as long as these pulses are periodic with n paired. And between different multi-carrier, like from the first multi-carrier to the second multi-carrier, if we use a root Nyquist pulse, we can guarantee the first multi-carrier signal and the second multi-carrier signal, they are orthogonal with respect to the delay. So between different multi-carrier, they are orthogonal with delay. Within the same multi-carrier, they are orthogonal with a Doppler. That's why we have this orthogonal delay Doppler division multiplexing. That's a very interesting way to look at the ODDM. So in summary, we say the ODDM combines the orthogonal Doppler division multiplexing, ODM, and orthogonal delay division multiplexing, or lowercase dm. So orthogonal Doppler division multiplexing, the total bandwidth is 1 over nt, because the subcarrier spacing is 1 over nt, and you have n subcarriers, so the total bandwidth is 1 over t. And you can have, if you don't have this bandwidth constraint for this ODM, any pulse as long as it captures the duration of NT with a period T, can guarantee these subcarriers are orthogonal with each other. A simple choice could be a rectangular pulse with a duration of T, similar to ODDM, which is widely used. But the disadvantage is you cannot multiplexing in time to improve the rate. So what we did in our ODDM actually is, if the bandwidth can be increased by m times from 1 over t to m over t, we can have orthogonal delay division multiplexing on top of orthogonal Doppler division multiplexing. So orthogonal delay division multiplexing has an interval of delay resolution is t over m. So if you just look at that, so if you only want to have orthogonal Doppler division multiplexing, and the waveform, the multi-carrier waveform is a top, you can use a triangle pulse train as its fundamental pulse, or you can use this Gaussian pulse train as a fundamental pulse, or you can use a rectangular pulse train as a fundamental. They can always guarantee this orthogonal Doppler division, multiplexing are orthogonal with each other. But in order to multiplexing different orthogonal Doppler division with the delay resolution of T over M, we definitely need root raised cosine pulses, the last one, to have different orthogonal Doppler division multiplexed. So this square root Nyquist pulse provides orthogonality with the delay resolution on top of the Doppler division guaranteed by the periodic pulse function. So the bandwidth occupants, if you consider the rectangular pulse, it has a large bandwidth consumption. Root raised cosine pulse provide a good trade-off between the time frequency spread. So the select root raised cosine pulse train as our DDLP in the ODDM. So that summarizes how ODDM was designed and how ODDM multiplexing different symbols in the same time and frequency resources. So with that one, we move to look at a few important properties of this ODDM. One is time frequency localization. And so let's take a look at why we need to look at the time frequency localization, because it is in the history, given by the theory of communication by the very famous pioneer, and Geber says the Heisenberg uncertainty, to analyze the Heisenberg uncertainty and to make any signal is realizable, we need to quantify and analyze the time frequency localization metric for the signal. So given we have a DDLP, we would like to find what is the time frequency localization. So it is to try to understand the energy spread of the DDLP in time, frequency, and joint time frequency domain, and try to verify whether it violates the Heisenberg uncertainty principle or not. So there are basically 4 metrics to specify the time frequency localization. One is a time dispersion, means a given signal in the time domain, xt, we try to find the standard deviation of the time domain response of the signal or the pulse, delta t. We can also find the frequency spectrum of the signal later on to find the standard deviation of the frequency domain response of the pulse, delta f. With delta t and delta f, we can also find joint energy spread in the time frequency domain, which is delta A equal to delta T, delta F. The Heisenberg uncertainty says that joint time frequency area delta A should be larger than or equal to 1 over 4 pi. 1 over 4 pi is also well recognized as a Geber limit. So we just need to find out what is the time frequency localization for our transmitted pulse. Another information we would like to know is the direction parameter, means whether the signal is more spreading in the time or more spreading in the frequency. That is another parameter we probably would like to do that. To figure out the the DDOP's time frequency localization. In time domain, we know what it looks like. It looks like a train of n subpulses. They are far away from each other by t seconds. So we have n time slots, n subcarriers, we have n subpulses. And we can also find the frequency domain response, UF, of this pulse. And in the frequency domain, it contains a train of m tones, and each of the tone is spaced by 1/t hertz. So that is the time and frequency response of the signal. With this time frequency response, we're able to work out the time dispersion, the frequency dispersion, the joint time frequency localization, etc. So I'm not going to the details of this mathematical calculation. I probably would like to share with you. If you look at these parameters, they are not near to any of the gamma limit. You can see this time duration, or the not duration, the time dispersion delta t is quite large. The frequency dispersion delta f is also quite large. And as a result, the time frequency localization delta A is large as well. Means the signal is widely spread in the time and the frequency domain. So that is one thing we would like to mention. So any insight we can draw from here, we would like to say the delta A is much higher than 1/4 pi, so does not violate Heisenberg uncertainty principle. So we say the signal energy is widely spread in the time frequency domain. So because the signal has multiple tones in the frequency domain, it also has multiple time slots in the time domain. So you have this cross-scattered signal. So if you look at each of these locally scattered region, it looks like well localized in the time frequency domain. But we have to be careful. This each localized, looks localized, cannot be realized in reality. So means this time and the frequency joint distribution has to be coexist. If you have multiple tones in the time frequency domain, you have to have multiple pulses in the time domain. So that the DDLP looks like locally well localized, but it is not. And it is globally distributed. So in time domain, and each of the small region is very small, close to 1/4 pi. If you only look at each small region, it's very close to 1/4 pi, which means you can, if you do sensing, you can do very high resolution for sensing. Because the signal is distributed in the time slots and the frequency tones, we are able to provide full diversity for communications. So that's is the time frequency localization occupation of the DDLP. Now we know this ODDM have been proposed in last few years, and we talking to colleagues and collaborators, also industries. One of the interesting question always been, can we design system to implement this ODDM transceiver? How it looks like? So we did consider this question, and we say, okay, if we have this ODDM signal, can we directly implement as a multi-carrier modulation in an analog version? So yes, so to do that one, and for each delay, remember, in relation to each delay, you have n subcarrier multi-carrier signals. That means we can generate, if we have n data for else delay, we do multi-carrier modulation. Later on, we have this adder or mixer. Then we're going through this pulse shaper or time window specified by our UT. So that is only one multi-carrier signal with n subcarriers. We have m multi-carrier signals, they have a different delay. So we time multiplexing them with the delay difference of t of m, we can generate a signal xt. So that is what we have this ODDM. But if we directly implement this one, obviously you see, we need mn mixers. Each modulator is a mixer. And for each multi-carrier, we also have a truncator or time window. So we need n truncators. So implementation complexity is very, very high. So we can also have an approximate implementation for this ODDM signal. Remember, this ODDM is a multi-carrier signal. And there's a rich literature and talking about multi-carrier modulation, how to use IDFT to implement it, given by the Weinstein's paper in early 70s. And obviously nowadays, OFDM have been used this simple implementation, IDFT, with simple wise pulse shaping to implement it. So this principle is widely used. We can also use it for our ODDM modulation. So the implementation will be much like this one. And we have this for each multi-carrier modulation, we have n data symbols. We do n point IDFT. Later we do upsampling. Later we do staggering. It means addition of the signal. Then we do pulse shaping. The reason we do pulse shaping is because the Nyquist rate before you do pulse shaping and while you are doing pulse shaping are different. So when you implement that, and the upsampling stack addition can be implemented very simply by using parallel to serial conversion. And the pulse shaping can be implemented by using upsampling convolution with sample-wise pulse specified by the subpulse AT. Later, you have this DAC to convert analog signal to the digital signal to the analog signal. So this is a very simple implementation by using this digital implementation. But what I would like to mention, this digital implementation is approximate to the ODDM. It's not exactly to the ODDM. To specify that, we would like to have a look at the time and the spectrum response of the ODDM signals if we use a different implementation. To do that one, we go back to the fundamentals. What is the basis functions of analog and digital ODDM system? To successfully comprehend this ODDM and implement that, we need to understand from the equation later to analyze its spectrum as well. So different implementation can have different transmitted signal version. They are very similar, but they have a little bit of difference. So let's just say, write any modulation and of ODDM, and this per se could be analog or could be digital implementation. XDD is our digital domain, delay Doppler domain, symbols to be carried over the modulated signal. This phi is our basis functions to carry each of the delay Doppler domain signal. So it depends on you transmit the signal is analog or digital, you have different basis functions. So we would like to point out for analog ODDM signal, we are able to write it in the first equation. For digital, we are able to write it in the second equation. And if you look at these two basic functions, they are quite similar. And they all contain this pulse train AT. So it's given by the right-hand side. AT is our subpulse. And the T is our Nyquist crossing point, T over M, also is our delay resolution. TA is the total duration we truncated this subpulse. If we look at the analog ODDM, and the analog waveform can be represented by this, I hope you can see my curves showing this, the middle curve to show that is our pulse shaped by the exponential function representing the phase shift. That is our analog signal. But for digital signal, it's still the same subpulses or pulse train, but shaped by different phase shift. So we can say the base functions for the ODDM system can be characterized by subpulse train AT plus a phase term. The subpulse train are same for both analog and digital ODDM signal, but for the phase term, analog ODDM and digital are different. For analog, it's a time varying phase function. You can see slightly changed. But digital form, it is a sampled version. So it is a sampled version of time varying phase change. So that gives you a slightly different representation time domain. As a result, we also have a different representation of frequency response for analog and digital ODDM. So if you look at in the frequency domain, they also have an infinite train of tones shaped or enveloped with this A function. But analog ODDM, this A function is frequency shift or Doppler shift. Specified Doppler means for each Doppler message to be carried, the frequency envelope should be shifted. But for the digital implementation, the Doppler frequency envelope is fixed, does not shift. So that gives you different spectrum as well. So we can say the spectrum occupants of the two base functions are different. So the conventional UF is here for analog, and it is a shift for different carrier or different Doppler carrier. For digital, it's constant. So as a result, analog ODDM has a slightly wide bandwidth compared to the digital ODDM. It's always fixed, regardless of the Doppler subcarrier. So we say the power spectrum density of the ODDM signal and the analog signal. I'm not going to the much details. I'll probably just show you the last picture and to show. This is shows if we look at the power spectrum ODDM signal, if we have an analog ODDM implementation, the sideband is you have this staircase spectrum. The staircase different ways is 1 over T. But for digital implementation, you have this side lobe is not a staircase. The side lobe width is 1 over TA. TA is a subpulse duration. So that gives you different spectrum if you look at this ODDM signal in the frequency domain. So we say analog signal has stepwise out of band emission, but the digital, we have this smooth, but this bandwidth emission. On both sides, ODDM has a lower OOBE compared to OTFS-SIG. So that probably summarizes the different implementation have a different spectrum. And if I have time, I'll probably go into the last part to take a look at what is ODDM over general doubly selective channel and what is the performance. Particularly, I like to pay a little bit of attention to the equivalent sampled delayed Doppler domain channel, ESDD. And what is the relation between this equivalent sampled channel and the physical channel? And what are the implications and applications? So doing this delayed Doppler domain, and most of the researchers, and including us, when we talk about OTFS or ODDM, we consider this ODDM with a typical channel. A channel only have a few multipasses. Each multipass has an ungraded delay and ungraded Doppler. Nothing wrong with that, because that is what we started doing any modulation, started with a simple case. But one of the questions people always ask is, practical physical channels are almost surely off-grid. So if you give me a multipass channel, the delay and the Doppler most likely are off-grid. They are not totally on-grid. But for digital communication system, at the receiver side, before we do any detection, we will do a sampling. We do a matched filter, we do a low pass filter, and we do sampling. After sampling, what we see is a sampled equivalent channel, which you can see on the grid. Either it is on delay grid and Doppler grid. So that means when we do performance analysis, we usually consider an equivalent sample of the delay Doppler domain channel. The question is, what is the relation between this physical channel and the equivalent channel? To answer this one, and it is important for us to fully understand behavior of the delay Doppler domain modulation, also help us to understand how the channel estimation, the sensing can be done and for the communication and the sensing system. Particularly, I would like to say, for communication, what we care about is equivalent channel. As long as we have the equivalent channel, we can do the detection, demodulation, no trouble. But for sensing, most of the case, we would like to know the physical channel parameter, like what is the delay, what's the Doppler, because we cannot give ambiguity of a particularly and smeared delay or Doppler come from a multiple pass effect. So that is why we need to find the relationship between two of them. I will skip this one. I know this is important. Talk about the analog implementation, digital implementation of ODDM, because that provides a relationship between the digital implemented ODDM over general channel. General channel means we have a physical channel is not on grid for its delay and the Doppler. The delay and Doppler may be larger, not necessarily have to be on the spread. So to answer that question, we say at the transmitter side, any of your transmitter signal XMN, you have going through a transmitter, you generate a transmitter signal XT, you have to have a transmitter pulse, IT. Then you're going through your channel, which is a physical channel, off-grid, and specify your amplitude, delay, and Doppler, any number. So at the receiver side, you do pulse shaping or matched filtering, a conjugator minus T. Later you do a sampling, you got to receive the signal YMN. So from your delayed Doppler XMN theater to your received YMN theater, what we care about is the equivalent delayed Doppler domain channel HMN, means you look at the channel at the receiver M's delay, N's Doppler, compared to your transmitter signal at M tilde's delay, N tilde's Doppler. What is the relationship here? That is your equivalent sample channel. So we say we can write it in a general format. If you have a piece pass, you have to consider pass gain and the ISI coefficients, means in the symbol interference and also in the carrier interference. You also need to consider phase shift due to the CP, cyclic prefix. You also need to consider phase shift due to the propagations. So we are not going to the details. I think you can look at our recent paper and orthogonal delay Doppler division multiplexing over general physical channels. We are able to give a very general term of the delayed Doppler domain channel representation, HMN, M theater, and N theater. And your pass gain is very simple. Your ISI coefficient is specified, this G tau nu, which can be defined from the ambiguity function. But with this G actually is effective pulse describing the leakage due to the delay. Your ICI term, it looks like very complicated, but you probably seen this term in radar or in OTFS multiple times. Actually, it is directly like a kernel describing the leakage along the Doppler, means if your Doppler is not on the grid, how much you leak to the each Doppler grid. You also have this phase shift due to the cyclic prefix. You also have the phase shift due to the propagation delay. So that is very neat and the description from the physical channel. So here you have not many parameters. The physical channel parameter is just HP, tau p, nu p. And you have this equivalent digital channel H is only described by the physical channel parameters with your generator pulse, AT, and your matched filter, A star T. So that's a very nice equation. I skipped this one, the leakage from ISI and the leakage from ICI due to your delay and Doppler. Probably skip this.
We have 10 minutes left. We have already. Yeah. Thank you.
Okay, thank you. So we probably just skip this one. What would I like to show you a few important simulation results. So people care about what is the performance and for this ODDM and how different implementations and compare it is performance on practical channel. So we have some simulation result with 4-QAM message and M equal to, we have 512 delay and 32 Doppler shift, and we have T is specified 66.67 per second. And we have 4 different detectors. One is a message passing detector. That means you build this effect graph at the receiver. Another is a maximum ratio combiner by using this delay Doppler domain or delay time domain, this block triangle channel condition. You do interference cancellation one by one with the maximum ratio combining. Another 2 detector is successive interference cancellation with MMSE detector, hard decision. Another successful with soft decision. So let's take a look at what we see is a message passing receiver, the blue one, and the maximum ratio combining had this very high error flow. But with the MMSE detector, you are able to get much better performance. This is a beta rate versus signal to noise ratio for the system. This is considering perfect channel state information. Now, if we consider iterative detectors and we want to see which receiver has a better convergence, we can say message passing requires 6 to 7 iterations to converge to good performance, but MRC only requires 3 iterations to converge. For successful MMSE soft and hard, we only need 3 or 2 iterations. We can already converge a good performance. Those results are all for perfect channel state information. If we have imperfect channel state information, what we see is if we do channel estimation with pilot power is 40 dB over your noise power spectrum density or 35 to 30 dB. What we show here is if your signal to noise ratio for the pilot power is 40 dB, on the left-hand side, we see that performance is quite similar to the perfect channel estimation. And but if your signal to noise, if your pilot power reduces to 30 dB, we see the message passing is really not working, but other receivers still works, but not very good performance. This is for uncoded system. And there are also complexity. I probably will skip that one. And just given the time, I would like to stop here. I would say we provide a brief review of ODDM and the ODDIP, orthogonal delay Doppler, pulses, and DDLP. I should say DDLP, that's a typo here. Then we talked about this time frequency localization, implementation, and the spectrum, and their performance. While this is only the work in last couple of years, in general, I think for OTFS or ODDM, there are a lot of other works that need to be considered, or I would say it's a challenge, considering detection high complexity and how to scale the system with multiple antennas and multiple users. how you do resource allocation, how do you deal with latency, because you need to do a long frame, and how you do coexisting with the current 4G, 5G system, and how you do system adaptations. So a lot of research need to be done in the future. I also would like to thank my postdoc Akram and my PhD student Kehan, who together with my collaborator Jinhong from University of Wollongong in Australia prepared the slides for me, and without them I would not finish this one. I would also like to thank my collaborator and Professor Hailin from OMU Japan, and a lot of the ideas coming from my postdocs and PhD students previously who contributed this topic. Thank you very much for your attention. I would like to stop here, Shuanyang.
Thank you, Professor Yuan, for the great talk. In general, this topic is actually really relevant to our SIG, and a lot of things you have presented are very interesting to people, including me, myself. There are several questions, and I hope you have some time to answer. Okay.
I do have time, yeah.
Thank you very much. So I think the first question is actually on the slides page 45, when you are presenting the numerical results of the ODDM. Are they based on fractional delay or Doppler, or as you mentioned, you only care about the equivalent channel, so it's a integer?
Oh, good question. I think this is for the, I think if I remember, this is based on the EV channel, which has a fractional delay.
EVA channel, okay, I see. Yeah. So, and like a follow-up question to this is actually because it has fractional delay Doppler, and you were mentioning about this equivalence in sampling. So I'm a bit could you actually highlight on the equivalence of here? So when the channel has fractional delay Doppler, so what is the best way for us to study this problem? Shall we treat it as an integer, or we just look at the fractional cases?
Okay, very good question. I think for practical system, we should treat it as a fractional and find the equivalent channel.
Right. So for this equivalent channel, it's different from the integer cases.
Yeah, definitely. I think this work, we really need to find this equivalent channel.
Right. Okay.
Yeah. Then have this equivalent channel, you can do the delay Doppler domain detection. But I probably have to specify, although we consider EVA channel, I could be wrong. This work is done by Kehan in the early stage before we just working on this equivalent channel. Then I think the delay we consider the delay shift, what is called leakage Doppler. We consider only the maximum 2 Doppler shift leakage. Means not purely, not fully.
Right.
I hope you understand what I'm saying. Is we consider equivalent channel, but not a fully equivalent channel. There's some approximations there. Right.
But these approximations are adapted to the filters design, so it may have very significant contribution to the channel. Yeah, I see.
Yes.
Okay, that's great. And another question I have summarized is actually from page 31 when we are talking about DDOP.
Yeah.
Yes, actually, this is actually
one?
Yes, please. Yes, this is actually show a lot of similarities to this OTFS 2.0 and it's a transform-based OTFS. So I would like to know your view about these two kind of waveforms and the insights on implementation.
Okay, good question. We talked about the OTFS, initial OTFS, we call it that is a pre-coded OFDM. Am I right? But I think to be fair for OTFS, they have OTFS 2.0. And we are also studying this OTFS 2.0. I have to be careful. I have not fully comprehended that one yet. And my understanding is they probably somehow similar to our approximate ODDM in digital version.
Yes, I personally agree. Yes.
Yeah, but I don't know. I mean, I think we discussed this multiple times before.
Right.
I did ask you and others, what do you mean OTFS 2.0? Although they have a lot of mathematical equations, but we try to comprehend it. And so I think my point I would like to take that there's a rich literature for multi-carrier modulation. And my point is, if for engineers to implement that, we probably would like to use their terminologies and better for them to understand a new waveform.
Right.
So by doing that one, we try to build the link between what is ODDM compared to conventional multi-carrier modulation and how we build that one. After our analog ODDM, we provide a digital implementation of ODDM. It's approximate to ODDM, analog ODDM.
Yeah.
But for OTFS 2.0, in some cases, might be, I had to be careful here, might be similar to our digital ODDM. Yeah.
Yes, I agree.
But I need to, we can discuss this later and try to understand this is for the benefit for the community, also benefit for the collaboration for the future as well.
Yes, yes. I think this is actually really important because we also invited Hadani to give a presentation here a couple months ago, and he actually mentioned something very related to this part. Actually, I think what he mentioned is about the orthogonality as you are presenting about the DDOP here. He personally said that like a delay Doppler stuff is a bit is not a really practical orthogonal because the channel always give you some of the off-grid components, and therefore orthogonality at the transmitter side, of course, is important, but at the receiver side, it's really hard to maintain this orthogonality. So what's your view on this?
Yeah, this is a very good question. That's exactly, I think this, I would like to make this crystal clear. Yeah, exactly. And when we say orthogonality and for DDOP, we are talking about the pulse itself.
Yes.
Means if we have this pulse, we can guarantee this transmitted signal, they are orthogonal. The transmitted signal, they are orthogonal at the transmitter side.
That's right.
They are orthogonal with the delay and orthogonal with the Doppler. But obviously, if you have a channel, and I think I go to this one. If you have a channel, this channel only give you one path. If I think give me 1 second. If the channel, so I use this one. If the channel give you only one path, either this path has a delay shift or Doppler shift, whatever delay and whatever Doppler shift. As long as we transmit ODDM, given this one path, at the receiver side, our signal are still orthogonal. But if you have a channel, give you multiple passes, say 2 passes.
Right.
Even your transmitted signal are orthogonal. At the receiver side, you may not be orthogonal, or most likely you are not orthogonal. So it means transmitted signal is orthogonal, but because you have multiple passes at the receiver, you are not orthogonal.
I think so. Yes.
So, but if your transmitted signal, so that's the, but people may ask, if the received signal is not orthogonal, what is the point you design a transmitted signal is orthogonal? So my answer to that one is, so if your transmitted signal is orthogonal with delay and Doppler shift, even you going through the multipath channel, receive the signal, give you smeared delay and Doppler multiple versions. Your interference in some sense is still minimal because your interference is only introduced by the channel, not by the signal itself.
That's right, yes.
So if your transmitted signal is not orthogonal itself, going through the channel give you interference. at the receiver side, you have interference. You have two types of interference. One interference is due to the channel introduced to you. Another type of interference is because yourself at the transmitter side are not orthogonal with each other. You yourself have interference with each other at the receiver as well.
Yes.
So you have two types of interference.
Right.
So this is analog to the conventional single transmitter, single receiver. Why we design root raised cosine pulse? Because we want to make sure there's no intersymbol interference given through the channel.
Right.
Yes, I want to, dear professor, I want to add one more point about this orthogonality at the transmitter side. Given this orthogonality at transmitter side, it can simplify the receiver design. You can like decouple the channel equalization and the decoding, like two separate paths. Like the interference comes from channel. We deal with it with the channel equalization, and after deal with the interference comes from channel, we can perform in the decoding based on AWGN channel. Then, yeah, it's just one point.
Exactly. Yeah, it's Zhiqiang, I think.
Yes, Professor. Yes.
Yeah, okay, thank you. I think that's another excellent point. So I did not elaborate, but Zhiqiang elaborated very well. It is very useful for detection. I guess probably it is more useful for sensing.
Mm-hmm.
You think about it, and if you want to sense some environment, at the receiver, you need to decouple, using Zhiqiang's word, decouple the interference from the channel or interference from the signal itself. If you want to do something, you want to find the environment parameter. You don't want the signal interfere itself, am I right?
Mm-hmm. That's right.
So have this delayed Doppler domain orthogonality, this DDLP, really helpful. And actually, I think in my previous talk, I didn't mention this one. If you take a look at this DDLP, and it is nothing but the pulse train for the pulse rate that people has been using it for a long time. Mm-hmm. So it is naturally, I mean, you can do integrated sensing and communication. I think that's probably, yeah. So you can easily use this signal as a transmitter pulse for pulse rate. Yes,
I agree. And actually, I would also like to make one of my personal understandings for this part is I think potentially what we can do is also consider the effective channel with respect to both the transmitter interference and the channel interference. And then we can try to design a pulse that is actually that can minimize the interference from both of the aspects. Potentially this, I'm not sure if that will work well, but certainly it may not be orthogonal, but I'm not sure how this non-orthogonality actually contributes to the minimization of the interference. But I think it's very important that people here are focusing on the pulses, which is personally my interest as well.
Yeah, I think that's a good point. Thank you, Shuyan.
Thank you, Professor. And another question actually is still regarding to this DDOP is on your page 22.
Page 22, let me go to there. Is it coming?
No, it's 19, it's 20.
Yeah, okay.
Yes, I think in your presentation, you mentioned about the periodicity along different pulse trains, and this is something necessary to maintain the orthogonality in delay Doppler. However, I would like to ask your opinion on particular this picture on when you are showing the frequency domain, that is the capital UF, which is a mask filter on a lot of pulse trains. And my understanding is here is like when you are having this kind of a masking filter, the pulses at the beginning and the ending part, they are not periodic anymore to the other pulses. So do you think this will violate the orthogonality in delay Doppler?
I'm not quite sure what you are talking about. Oh, I see. I roughly know what you are talking about.
Yes.
I don't think so violates. And you see, this is the spectrum. It is a masking there, right?
It's masking, yes.
It is a masking. And Shuang, I probably could not directly answer you, but sorry, I could not give you much detailed explanation. My understanding is you will not, because we proved that one. It is
okay.
On the theoretical level, we proved this orthogonal with each other.
Okay,
so why you say would? Do you have any explanation why it would?
Well, intuitively, I would say that because particularly due to this roll-up parts, you have a less energy at these points at these parts, and therefore there's some pulses that has a smaller amplitude, and this is the reason why this is no longer periodic here. So
you mean the tones? You have some tones.
Yes,
they are less energy. I'm right.
Yes, for example, the tone at frequency minus I'm over 2t and I'm over 2. Yeah, minus that part.
Yeah, so I know what you are talking about. I think you probably, do we have a aliasing principle here? If we consider aliasing principle, they will combine together to have the same tone, am I right? The same amplitude.
I'm not really sure about the details here, but I think no matter what, this actually only consists of a very small part of your whole signal. So my understanding is like if you have this masking is actually very long, potentially it's the same as your bandwidth, then this will give you a minimum effect as long as the access band is not too large. That's my understanding. But still, that introduces some of the approximation, so it's not too much a big deal, I think.
I think it's still the aliasing. I think if you consider aliasing and the effect, maybe still orthogonal. But let me get back to you later. Okay.
Thank you very much, Professor. Okay, we only have one last question. It's about the general topic. So you have presented the ODDM, and as you may know of, actually, we have a lot of new waveforms recently, and we actually invited some of the speakers here. And so I would like to know your point about this new developments on like waveforms, including, for example, ODDM, OTFS, and potentially there are AFDM and OCDM, and even I see that our MOXIE friends are also here. So there are a lot of different new waveforms. What's your perspectives on this?
I think it is good to have multiple waveforms, because, when people are working on different domains, we can borrow concepts from each other. We can have relevant, good discussion to exchange ideas. I think it is a good thing. And obviously, in our group, we are also studying these new waveforms to understand what is the difference and what kind of new ideas they bring to there. I think I don't have any we just started looking at the papers and including OTFS 2.0. We don't have much details and to provide there, but I would be happy if there's further discussions in your special interest group. Somebody can present some result, then have further discussion. I think it's a good thing in general. That's probably my the best answer I can provide. And we would like to see more interesting discussions on that one. We have a little bit of look at, we probably can share a little bit of work on OCDM. And we have a little bit of understanding of OCDM, but it's kind of the user chirp signal, right?
Yes, chirps.
And we try to compare OCDM with OFDM. What is the similarity? What is the difference? And we find that OCDM is pretty much, it is kind of multi-carrier modulation, similar to OFDM, but only in certain channel conditions. Say if the CP length is not as long enough as the delay spread of the channel, OCDM provide better performance. That's the only thing we find. But it is not a new thing because that was also reported in the initial paper.
I see, right.
So that is what our understanding now.
Okay.
Do you have any insight on this one you would like to bring to discussion?
Well, there are for me, I think there are all very interesting waveforms, and particularly for OCDM and AFDM, I think they have some similarities. And I have also seen some new waveforms based on some like alterations of these waveforms. So I think in general, using chirps is an interesting idea. And however, so far it's not clear to me is that how this is from a very rigorous perspective, have some potential performance gains in terms of computation and potential distancing. So I think it's in general very interesting topic as well. Okay, thank you, Professor Yuan. I think I'm now actually persuading all the speakers to give one sentence which is summarize this waveform. So what do you think is the most exciting or the killing properties of, for example, ODDM here? Just one sentence will be enough.
I guess nice, I mean, orthogonality with respect to the delay and Doppler. And we have this DDOP,
right,
and has a very nice feature, could be explored for the sensing and the communication.
Yes.
Okay. We expect more people to work on this one.
Thank you. Thank you. I think